Right, in this video, this is AP Calculus ABB, Unit 5, Lesson 6. We're going to continue working with areas under rotation or volumes of rotation. In this video, I want to address two issues. One is what happens when we rotate horizontally, and say about the y-axis or some other vertical line. And the other is, what if we rotate about a line that is not one of the axes, either the x-axis or the y-axis? So here's the problem I've got. I've got a graph, a shape that is the y-axis, or the line y equals x. Let's do it this way here. The line y equals x. And the line y equals x squared, just like we've been working with. Okay, but in this case, we're going to rotate about the y-axis. We're not going to rotate about the y-axis. We're going to rotate about a vertical line somewhere other than the y-axis. So let's draw our shape here. Let's just go about to 4 here. So 4 grid marks is 1 here, okay? And we're going to take this shape here bound by y equals x and y equals x squared. Okay, y equals x squared. And we're going to rotate it around the line x equals -1. Okay, x equals -1. So this is our axis of rotation. Okay, as you can imagine here, this is going to spin around so that the shape is extended over here. And I did not leave enough room. Cool thing about this is I can, oh, there we go. I can move things. Okay. All right, and so let's graph this here. Or draw the sketch. It's kind of fun drawing these. To draw stuff in 3D. Okay, and so the shape after rotation on the left side here ends up over here. And what we get is this solid of rotation that looks kind of like a bowl. Okay, and in fact, let's there we go. Okay, center it. Flatten it. Okay, let's draw it in green here. So we've got this circle as the base, and this circle as the top. Oh, I didn't draw it far enough again. Okay, let me fix that. Because that'll drive me nuts. There we go. There we go, and like this. Okay. Top circle like this. All right, there we go. Okay, so there's our solid of rotation. And these are our cross sections. So let's find the cross section of a washer, or the area of one washer. Okay, and we'll just pick a random slice in the middle. Here's the outer circle. Okay. And its thickness, delta y. And the inner circle, with its thickness here, delta y. Okay. And there's our washer, kind of a thin washer. But what is the volume of the washer? Well, the volume is the pi times the big radius squared minus the little radius squared times the thickness, delta y, right? Delta y is the thickness. So what is big R? Well, we need to solve these for x. So this is y, instead of y equals x, it's x equals y. And instead of y plus x squared, it's x equals square root y. And square root is the outer r, so big R is square root y. Actually, it's not. Big R is the distance. Now, here's where it gets a little complicated here. The distance between -1 and the outer radius, outer rim. So that is R, or that is root y plus 1, because we have to go an additional 1. So 1 and root y. So this is, big R is 1 plus root y. Likewise, little r is 1 plus y. 1 plus y. Okay? And that's really important to understand here, that this distance is y, and this distance is 1, so it's 1 plus y. Okay? And let's substitute that. So the volume is pi times big R squared. Big R is 1 plus root y. Minus little r squared, 1 plus y squared, delta y. Okay. And let's set up the integral. So now we have our volume expression. So our total volume of rotation is pi times the integral, just pulling the pi out from 0 to 1 of, okay, and let's go ahead and multiply this out. 1 plus 2 root y plus y minus 1 plus 2y plus y squared dy. Just doing a little algebra in the process to save ourselves a step or two. Okay, distribute the negative sign. That makes this negative, and this negative. Okay, so pi times the integral from 0 to 1 of, let's do it in order, in descending order of exponents. Y squared, negative y squared. Negative 2y plus y is negative 1y, negative y, and plus 2 root y, and negative 1 and positive 1 cancel out, dy. So volume is pi times the integral of negative y cubed is negative 1/3 y, or y squared, negative 1/3 y cubed. The integral of negative y is 1/2 y squared. The integral of root y, think root y to the 1/2 is y to the 3/2 divided by 3/2, so 2/3 times 2/3. 2/3 times 2. 2/3 times 2 is 4/3. 4/3. That looks too much like a y. 4/3 y to the 3/2. Okay, I'm just going to write y to the 3/2. It's actually y cubed, square root of y cubed. From 0 to 1. And luckily 1's easy to insert. Pi times negative 1/3 minus 1/2 plus 4/3. Yep. And 0 is just, the inserted is just 0. So I'll get a common denominator, 6, 6, and 6. This is 2 times 6, 2 6, 3 6, negative 2, negative 3, and 3 times 2, so 4 times 2, 8 6. 8 minus 2 is 6 minus 3 is 3. 3 6 is 1/2, so pi divided by 2 units cubed. Okay, and this deserves a little quick check with a calculator to make sure we got it right here, using our numerical integration option here. So the integral from 0 to 1 of, and I'm not going to do the algebra here, so we're just going to do 1 plus square root y. When you're doing a calculator check, it helps to eliminate as many possible sources of error. So don't take the time to simplify dy. Oh, 0.5. I forgot the pi. Yeah. Okay, and pi divided by 2. It's the same thing. Okay. All right, so it does check. All right, so a couple of ideas, things here. You have to be careful about, especially if you're not rotating about an x or a y axis, careful about what the big radius is and the little radius is, and express those in terms of what you know. And then solving for x to integrate on y is the other big idea.